on Monday, we talked about double sideband suppressed carrier modulation. So the modulation process is actually very simple. Just multiply the message signal with the carrier signal, and you get the double sideband suppressed carrier AM or amplitude modulated signal. Okay, that is for modulation. And then for demodulation meaning we want to recover the message at the receiver. Actually, it's also very simple. So what we do is at the receiver, we actually just need to multiply again, all right, the incoming signal, which is your AM signal, with a carrier signal. Okay, this carrier signal is the same carrier signal that we use at the transmitter or at the modulation process. Yeah, and this is called synchronous detection, right? The word synchronous is actually suggesting that this carrier signal that you use at the receiver must be synchronized with the carrier signal at the transmitter. All right, synchronized in the sense that the frequency must be exactly the same. All right, any phase angle must be exactly the same as well. All right, that's what synchronous means. So after multiplying these two signal, all right, the product, I call it V naught T, all right, and then the product of these two signal, we pass through a low pass filter, and that will give us the original message back. Okay, so the recovery process actually is very, very simple. So let's go through some mathematical analysis to actually see how is it possible. So again, recall the double sideband suppressed carrier signal equation is VAMT. All right, from previous few slide, we know that the magnitude is VMVC over 2, and we have a lower sideband component here, and we have an upper sideband component here. Yeah. Then the local carrier, we use the same carrier signal at the transmitter, which is VC cos omega CT. Yeah. Then we multiply these two together. All right. Here, this is your VAMT, and this is your VCT local. We multiply. Dot means multiply. Yeah. So if you perform cross multiplication, then you get VNVC square over 2. Right, VC square basically have this VC, another VC coming in. And then you have cos omega CT minus cos omega NT. This term multiply with cos omega CT. That will give you this term here. All right, then you have the plus one, the upper sideband component, multiply with the carrier frequency or the carrier signal. Then you get your second term here. Okay. Then again, you can see this is another cos x cos y. All right, another cos x cos y. And therefore, for this, you're going to have, okay, so for this is your x here, and this is your y here. All right, so what you have is omega ct minus omega mt plus omega ct. We give you this term. All right, minus omega ct. This is x minus y. All right, and this is your x plus y. Yeah, and again for the second multiplication of two cosine signal, and let's say this is a and this is b. So what you're going to have here is basically a minus b, and this is a plus b. All right. So every cos A cos B will give you cos A minus B plus A cos of A plus B. Okay, so if you were to simplify the terms, right, omega ct here minus omega ct here will give you cos of minus omega mt. All right, cos of minus omega mt, and this one will give you cos omega ct plus omega ct will give you cos 2 omega ct minus omega, which is this term here. All right, this one will give you this term. And here we have another cos omega ct plus omega mt minus omega mt. So this one will cancel and give you cos omega mt only. All right. Well, the next one here, you have omega ct plus omega ct. This will give you the 2 omega ct plus omega mt. All right. And here I have cos. From here I have this. I have this term and this term gone. So meaning I have cos minus omega mt here. All right. Remember we actually look at the cosine function. Cosine function basically is an even function. Which is your cosine. All right. That means the cos of minus x is equal to cos of x, right? Therefore, cos minus omega mt, basically I can convert it to cos omega mt. So that will give me 2 cos omega mt here. All right. So you can see that this is actually my baseband signal. All right. This is the baseband signal. And then I have a component at 2 omega c plus omega mt, another component at 2 omega c minus omega mt. All right. So that is V naught T here at this point. Yeah. And if I were to pass this signal through a low pass filter, you know what is a low pass filter? Basically, a low pass filter will pass a signal at lower frequency through, and then a signal at high frequency will be blocked, right? So now we only want our signal here. This is our baseband. We want this baseband. We don't want this one. We don't want this one, right? Therefore, we block these two. Yeah. So your low pass filter, you have to design such as the cutoff frequency is actually greater than omega m, but less than 2 omega c plus omega m, right? So that it block these two. Yeah. So normally maybe it's omega m plus something like it gives some omega m plus something, just a bit of a room. All right. So that you have recover your omega m here. Okay. So that will allow your baseband signal to pass through and block the rest. So that will give you your original message back. Okay, original in the sense that you got the all the frequency component back. The amplitude, of course, is maybe lower or higher, depend on what is your VC. Okay. Hello, are you following?
Yes.
All right. So then let's move on to look at how what actually happened in the frequency domain. All right. So now let's look at let's recall what happened on the transmitter side. On the transmitter side, let's say I have my message signal. Right, a message signal. Let's say I use a single frequency component. This is my FM. This is my minus FM or omega. I was using omega just now, right? Okay, let's change to omega. All right, this is omega m. This is minus omega m. All right, so let's say in the example I was using cosine signal. So this is my VMT and this is my VM omega. All right, my message signal. Okay, and my carrier signal is a higher frequency. Again, I use a cosine. So therefore, let's say my omega c is here. All right, and then my minus omega c is here. Again, it's a cosine wave, so I have a 2 delta function, right? So that is for carrier. This is my VC omega. Then the double sideband suppressed carrier signal. All right, I will have at omega C, suppressed carrier, meaning that there is nothing at the carrier frequency, but I have omega m here. So this, when we multiply, remember when we multiply two signal in time domain, in the frequency domain, we're actually convolving them, right? Convolve meaning I shift the entire spectrum of my message signal to center now at the carrier frequency. All right, so that means I'm going to shift minus omega m and this omega m so that it's centered at omega c. All right, so what I have here is these two, right? This is omega c plus omega m. This is omega c minus omega m. Okay, and same thing because I have two impulses here. So this one shift onto the positive frequency. I also have another set that is shifted to the negative frequency. So that means I have this, right? The omega c, this is minus, sorry, minus omega c plus omega m. This is minus omega c minus omega m. Right, this is my double sideband suppressed carrier signal. Okay, this is what happened at the transmitter. So what happened at the receiver? So this signal, let me copy over here. Oops. Okay, I have here at omega c, I have this one here, and I also have minus omega c, I have a pair here, right? So this is my, again, this is my double sideband suppressed carrier signal. Now at the receiver, I'm going to multiply it with the carrier, and the carrier frequency is at omega c. Right, so that means I have the carrier signal has two impulses, one at omega c, one at minus omega c. Okay, this is my carrier again. All right, so now I multiply these two signals together. That means in the frequency domain, I actually convolving them. So convolving them, that means I am going to shift this entire spectrum here so that it's center at omega c. All right, so that means the zero here will go to omega c. So the omega c plus omega c will go to 2 omega c. All right, so that will give me, let me draw a bit longer. Right, this is omega c. This will be 2 omega c. So 0 will go to omega c, right? And then this omega c will go to 2 omega c. So that means I have this one here. Yeah. And what about this one? Minus omega c, right? I actually, with 0 move to omega c, minus omega c will move to 0, right? Everything shifted. So plus omega c will move to 0. So I have here, this one. Okay, this one come from this one, shifted with it to this omega c. Yeah. Now, what about this one? Okay, I have another component at minus omega c. So for minus omega c, again, I shift the entire spectrum to center at minus omega c. So now 0 to go to minus omega c. All right, with 0 go to minus omega c will go to minus 2 omega c. All right, just plus, okay. So minus omega c plus minus omega c, you get minus 2 omega c. Yeah, again, I have a set of impulses. Okay, then what about this one? This one at omega c, I shift it down by minus omega c. Omega c minus omega c, that will give you 0. So again, this one will here. So these two overlap, we got double. All right. And then, so what is this frequency? Remember, this is omega c plus omega m, right? Omega c minus omega m. So therefore, this will be omega m. This will be minus omega m. All right. So this is the baseband signal I'm talking about. All right. If you refer back to your previous equation, yeah, this will be your baseband signal here. Our baseband signal here. This is omega m. Then we have this 2 omega c plus omega m. We have 2 omega c minus omega m. All right, is this 2 here. This is plus 2 omega c, 2 omega c plus omega m. This one is 2 omega c minus omega m. So we have these 2 here. All right. So you can see that this our baseband signal can then be easily recovered by passing through a low pass filter. So a low pass filter, that means if my low pass filter I design it such that it actually allow these two components to pass through, then I can easily recover my omega m. Right. So this is a low pass filter. Yeah. And normally omega c is a lot higher than omega m. So your low pass filter design can be quite relaxed. Nevertheless, if you want to reduce the noise, then you have to maybe tighten a bit your low pass filter. Okay, clear.
Okay.
So that is your. Let me jot down. What is this? I need to switch back to my color. So this is the demodulated signal. Demodulated signal. All right, so you can recover this one from by using the low pass filter. All right. Any questions here before I move on? No? No? Right. So this slide actually show you how we can multiplex. We can multiplex multiple signal together, right? And this case is frequency division multiplexing, all right? Because we are using a carrier. So for carrier communication, we normally use frequency division multiplexing. So now, this allows us to actually transmit many AM signals together. So let's look at what happened at the transmitter here. So now I need to transmit in this example here, I need to transmit 3 messages, X1, X2, and X3. All right. So what I do is I actually modulate X1 with a carrier with a frequency omega 1. All right, this is my carrier, and that give me Z1. Yeah, okay. On this slide, okay, if you are referring to your slide, please change this one here. I think I put X1, X2, and X3. Please change it to Z1, Z2, and Z3. And same thing here. All right, please change on your lecture notes. All right, so X1, what is the frequency spectrum of X1? All right, the X1 frequency spectrum look like this. All right, look like this. So this is your X1 omega or J omega. Let's look at omega. All right. So now I multiply with carrier of frequency omega 1 that give me Z1T. All right. So Z1T, if I convert into frequency domain, that will give me Z1 omega. All right. So what happened is again, when you multiply the xt with the carrier of omega 1t, so the spectrum of x1 will be shifted to center at omega 1, right? We have learned from previous uh, slides. All right, so x1 will be, the spectrum of x1 will be shifted to center at omega 1 because I use omega 1 as my carrier frequency. Okay, though that is the spectrum of z1 because z1 is a product of x1 times this carrier number 1 here. Okay, and then for x2, x2 is message number 2, information number 2, and this information, the baseband frequency spectrum looks like this. All right. So for X to transmit X2, I multiply it with a different carrier. This carrier have a frequency omega 2. All right. So what happened in the frequency domain is I'm actually shifting the baseband spectrum of X2 so that is centered at omega 2. So this is omega 2. All right. And this is minus omega 2. Okay. Same thing for signal number 3. All right. Message number 3. I multiply with the carrier with frequency omega 3. Yeah. And that will give me Z3. So Z3 is going to be centered at omega 3. Yeah. So I add them together. Basically, this is how the spectrum is going to look like after I add these three, the spectrum of these three signals. That is what happened at the transmitter. Okay. So that means what you see here, you can see here, we actually combine, right? We actually combine these three signals together and then we transmit them. Yeah. The reason for the fact that we use different carrier frequency to carry these three different signals, that means the spectrum of these three signals do not overlap in the frequency domain. All right. This one you must make sure. Yeah, your omega 1, omega 2, omega 3 must be chosen in such a way that these three spectrum do not overlap. If they overlap, that means your signal is distorted. You can never recover. All right. And in practice, in practice, actually, we provide a guide band. A guide band meaning we had a gap between these three. Yeah. So that again, that is to make sure it does not interfere, and then it's easier for us to filter later on. But then for concept wise, this is how we actually perform frequency division multiplexing. All right. We actually we actually send or transmit different message using different carrier frequency. Okay, so that is for frequency division multiplexing. Then what happened at the receiver? Okay, so the receiver, depending on which signal the receiver want to receive. All right, it's just like you listening to radio. You select the radio station you want, right? Yeah. So how for you, it's just a press on the button or you turn the knob, then you change your station in it, right? In electronically, what happened? Electronically is when you actually turn your knob or when you press a search button, you are actually changing the carrier frequency at the receiver here. All right. So depending on which channel you want to tune to, all right, in this case, which message we want to receive here at the output, we actually adjust our the carrier frequency at the receiver to match, all right, to match the frequency where we transmit the signal. Okay. So in this example here, I want to receive signal X1. All right. So what I need to do is I need to adjust my carrier frequency so that it actually match with the carrier frequency that was used to carry message number 1, X1. So again, this is my omega 1. So here my omega C is equals to omega 1. All right. So I have in the frequency domain, I have another version here at minus omega 1. Okay, so I multiply, all right? I multiply the incoming signal ZT with cos omega CT. So again, when we multiply in time domain, in frequency domain, we convolve the signal, isn't it? We just shift the signal, right? We shift the signal. So let's look at how when we convolve these two, how the shifting take place. Let me change my color. Okay, so now I have, I better switch to highlight. All right, so I have this one that I want to recover. All right, so that means omega 1, all right, or rather the whole spectrum, if you look at the whole spectrum of Z, yeah, then when we are convolving Z with the local carrier, we are shifting the entire thing to center at omega 1. We're also shifting the entire spectrum to center at minus omega 1, right? Yeah. So that means if you just look at x1 that you want, omega 1 minus omega 1, right? So that means everything will center at 0, which is this one here. Yeah. And also this minus omega 1, all right, plus omega 1, then you get 0. Again, it will center around here. Okay. And what happened when you shift this whole thing? You get another version here. This version here, this is at 2 omega 1. This is at minus 2 omega 1. All right. So in this case, we actually brought the spectrum of the signal or the message that we want back to baseband, which is this one here. Because we want to recover x1, isn't it? So you bring it back to here. Yeah. So what you do next is you pass it through a low pass filter. All right, pass it through a low pass filter, and that will allow all the frequency component of x1 to pass through the filter. The rest will be blocked. Then you recover your x1 here, okay, which is the original version of x1 that we transmit. Can ah? Hello? If you have question, you better on your mic and ask because I don't know what's happening if you actually just type your message in the chat box. I'm not seeing the chat box right now. Can ah? Right. Good. So if you same thing for the same with the same concept, if you want to receive, let's say I want to receive message number 2 at the receiver. All right. I don't like 1FM. I want to listen to my FM. So what you do is FM and AM is actually similar in that sense that you actually tune at the receiver. So you tune to a different, you adjust your local carrier frequency so that it match omega 2. All right. Then the carrier signal at the receiver will have your spectrum at omega 2. All right, at omega 2. Again, when you convolve these two spectrum in the frequency domain, and what you have is this omega 2 spectrum will be shifted to the center. All right, will be shifted to the center. And this one also will be shifted to the center. Yeah, of course, you have another version at 2 omega C here, plus 2 omega C and minus 2 omega C. But what we're interested is only the center, which is our baseband. All right. So this thing here will be shifted to the baseband. So what you have here is this version now, right? The sharp peak is in the center, and then the lower peak is here. No, sharp peak in the center, lower peak is here, yeah, and then the curved one is here, and so on. Right. So you shift the sharp one back to the center if you want to receive Z2. Again, same concept. The low pass filter will actually allow the baseband spectrum to pass and block the rest. Yeah. Okay, so let's move on. Okay, so as far as double sideband suppressed carrier is concerned, you look at the demodulation process. It's actually very easy. and also very cheap. Right? Why easy and cheap? Because all you need is multiplier and filter. Yeah, multiplier and filter are very cheap components. However, all right, it's not easy to have the exact carrier at the receiver. All right. Remember, for the demodulation process to work, you need to have the carrier at the receiver to be in exact same phase as the carrier at the transmitter. All right. Provided the signal was not distorted and was not phase shifted by noise again. Then if these two are in the exact phase, exact frequency, yes, it works. Yeah. What happened is in practice, it may not be easy for these two to be in same phase. All right. And the worst thing is um, in the channel itself, there are noises, there are distortion. All right. And then that will actually cause your AM signal when it arrive at the receiver to be phase shifted. Okay. Distortion is not that bad, but phase shifted will be actually uh, cause some damage to your signal. So let's look at what happened when we have phase of our signal being shifted by noise. Okay, now we have YT. What is YT? YT is this one, the product, the result of the multiplication at the receiver. And XT is our original message. This is XT. So multiply with cos omega CT. So this gives us our ZT, which is the one we transmit, right, at the transmitter. This is your double sideband suppressed carrier signal. We multiply these two, we get it. And then let's say I did everything arrive at the receiver, and then the receiver carrier has is phase shifted by this amount. All right, let's say it's phase shifted by this amount with respect to the incoming signal. So we multiply it with the incoming signal. Okay, again, you see here, this is cos A, cos B, or cos X, cos Y. All right, cos X, cos Y. So again, if you apply our trigonometry identity, then you get half of cos of the amount of phase shift. All right, plus half of cosine of 2 omega ct plus again the amount of phase shift that we have. All right. If we pass this YT through a low pass filter, this one will be gone. Right, we are left with this. So our YT will be half of XT, all right, times the cosine of the phase shift or the phase difference between the carrier component here with the carrier component um, in the double sideband suppressed carrier signal. Yeah. So the worst case is when the the phase shift is equals to pi over 2. All right, because cosine of pi over 2 will give us 0. So 0 multiply with whatever will give you 0. So you got nothing. You receive nothing. All right. Um, if the phase shift is changes with time, all right, then our signal will fade. It's actually quite common for AM signal to fade. Fade in the sense that sometimes you hear uh, let's say it's an audio signal, then the what do you call that? The signal or the voice will sound louder sometimes and softer sometimes, So that is a sign of fading in your audio signal. Okay. Hey, hello. Are you still with me?
Yes, miss.
Okay, then I move on. Then I move on. Yeah, okay. So how to solve the problem then? Okay. One way to solve the problem is to synchronize the sender and the receiver, is to make the carrier. All right, how to make sure they are synchronized is I send the carrier along with the message. All right, I send the carrier along with the message. So that means I take the message, I multiply it to produce a double sideband suppressed carrier signal, and then I add the carrier. All right, I add the carrier, and then I send it. Yeah. So that is how to send the carrier along. So this is a carrier. I add the carrier to the double sideband suppressed carrier signal that I produce here. Okay. Then let's go through the maths derivation again. So my carrier signal is again same as the previous one, which is VC cos omega CT. And my message is VM cos omega MT. So my VAMT, the output here, is basically the product of VM plus cos omega C. So cos omega C times Vn cos omega MT plus VCT, which is cos omega C, VC cos omega CT. All right. Then if I collect the terms, here I actually factorize it. Factorize what? VC cos omega CT. All right, I factorize VC cos omega CT. Then what I have left in the bracket will be 1 because this one I factorized already. Yeah. And then this part here will become Vm over Vc because the magnitude is only Vm. So because I factorize out Vc, so I have Vm over Vc here and cos omega mt. All right. And what is Vm over Vc? Vm over Vc is the modulation index of Am. All right. Vm over Vc is the modulation index of Am. All right. So let's move on to expand the equation so that we can see the sidebands. All right. So what we do next is we expand this equation over here. All right. So again, you can see I have cos x, cos y, cos x, cos y. All right. So what I have is cos x minus y, cos x plus y. Yeah. So Vm become Vm over 2. All right. Vc cos omega Ct is a stay. This one remain, no change because we just plus only. Yeah. So therefore, in this AM signal now, we have lower sideband, we have upper sideband, we also have carrier component here. All right. That means we are sending the carrier along with the signal, the modulated signal. Okay. Can Can, good. So positive. Okay, so another way, so I actually derive the equation this way so that I get here. All right. There's another way also to proceed with this equation. Right here, instead of factorizing BC cos omega CT, if I factorize cos omega CT, what do I get? I get VC plus Vm cos omega mt, right? Yeah, engineering always play with equation on, right? So now I play with equation and see how I can do things easier. So now I factorize cos omega CT, then I get this thing. So what it means here? What it means here, basically I can realize this, I can actually, instead of doing this, implement this, I can actually implement this another way. So what I have is I send the message, I plus first. All right, instead of multiply first, I can add first. What do I add? I add with the VC. What is VC? VC basically is a constant, is any number. So in electronic, a constant is a DC value. All right, I add first, then later I multiply. I multiply with what? I multiply with cos omega CT. All right, so that will give me the VAMT as well. All right, So there are actually two ways to realize this circuit. Yeah. And okay, now if we look at the AM equation, right? Let's come back to the A equation. We have lower sideband, we have upper sideband, we have carrier. So the name for this AM modulated signal is double sideband full carrier. All right, full carrier. Full meaning we send the entire carrier along, which is this one here. All right, that's why it's called double sideband full carrier. All right. So what is this? Okay, if you want to express the amplitude of the upper sideband and lower sideband, the amplitude is given by Vm over 2. All right, Vm over 2, or you can express it in the modulation index term by rearrange this equation over here. All right, what is Vm? Vm is MAVC, isn't it? Modulation index times DC. So you can actually rewrite the amplitude in this way. All right, MAVC over 2. Okay, MA stands for modulation index for amplitude modulation. Later, we're going to have MF. MF is a modulation index for frequency modulation. All right, A stands for AM, F stands for FM later. All right, any questions on this slide before I move on? No questions?
No question.
Good. Clear, huh? Okay. Well, this slide need a very long explanation, and we have about 5 minutes left. So I think I will end the class here. All right, and I'm ready to accept any questions. But since y'all got no questions, then we end the class here. But the can the